questions, please type your questions into the box to the right of the screen. And I'll just start with a quick introduction of our speakers. So today we have two speakers, Ralf and Enrique. They both have a lot of knowledge and experience in this field. So Ralf is an architect. His career has taken him all over the world. He's worked in the UK and Germany before moving to New Zealand and working with Concrete New Zealand. So at Concrete New Zealand, as an architect, he provides concrete design advice and works on the standards and the building code. Also joining us today is Enrique. Enrique is a structural engineer and a lecturer at the University of Auckland. He has extensive knowledge in the concrete design, and he continues to lecture and research in this field at the university. So welcome, Ralf and Enrique, and thank you for joining us. I think I'll pass on to you, Ralf. We can.
Thanks, Emil. Thank you very much, Jafar. I'm very happy to be here. Welcome, everyone. I virtually find myself here in a beautiful concrete masonry building built of dark oxide-colored blocks. So as Jafar mentioned, I'm an architect with Concrete New Zealand, and I've worked 15 years in Germany and Ireland, commercial, industrial, residential projects, before I joined Concrete New Zealand 11 years ago to advise on concrete-related topics. And yes, today we have two presentations, each about an hour, presented by myself and Enrique del Rey Castillo, teacher at the University of Auckland's Faculty of Engineering. So I will talk about concrete masonry basics and designing to NZS 4229, a standard written with architects and designers in mind, to structurally design a masonry building without the need for an engineer. So before we hear from Enrique, then on engineered designs. So since there is not much masonry taught at universities, I thought I would start giving you a generic idea of masonry construction and then look at 4229, which helps understand how a masonry building structural capacity is assessed and designed. So here are my sections for today, and I will share my screen now. And the presentation should come up for everyone visible, hopefully. I just pull these to the corner, so hopefully it doesn't take away too much. I'm still here. So I've prepared a few chapters. First up, what is concrete masonry? The four parts which make a concrete masonry wall. Standards providing guidance to masonry construction, which are out there in New Zealand, which we can use. Foundation design then to 4229. Walls in general, grouting, shrinkage control, tolerances, beams, lintels, diaphragms, and bracing, and all the letter 2 design to 4229. I have to see how much time I have left, how fast we go through, because I would also like to talk a bit about the visual possibilities of masonry, because it's actually quite stunning material. Veneer construction, weather tightness, also a quick chapter on fire, sound, thermal performance. And then I would like to recommend some reading resources, all available from our webpage and the Concrete Masonry Sector Group's website. So starting with concrete masonry. So I take it there's possibly a different level of understanding here. So I will start maybe at the beginning. So what is concrete masonry? What does it consist of? The most prominent part would be the block. This block is about 390 long and 190 millimeter tall, and independent of the manufacturer of the block. If it's block shop, Bowers Brothers, Firth, Mitchell, or Weiblock, they are always the same dimensions, which is pretty handy. There are various widths. The 90 millimeter is non-load bearing, the other ones are. So that's the actual size. And since those blocks are bonded together by 10 millimeter of mortar, we also talk about nominal dimensions. So 390 by 190 makes then 400 by 200. So bonding, there's always a vertical and horizontal mortar joint. Then, unlike in Germany, where I'm from, as you can hear my beautiful accent, there is structural steel required. In Germany, we don't need that. We just put one block on top of the next, bonding together with mortar, but we don't need rebar. We need rebar here in New Zealand because of the earthquakes. And to bond the rebar to the block, we then fill those cells. We use grout and very fine concrete. So we can only fill the concrete where there's rebar. That would be then called partial fill, or we fill all of the cells, which is more common. And then we talk of fully filled concrete masonry walls. So yes, I was talking about the standard dimensions. However, the concrete masonry block manufacturers make it extremely easy for you. They also provide off the shelves half length, half height blocks, corner blocks, and even sill blocks with a rebate and a sill already in place, capping stones, and blocks to place your horizontal rebar for lintels and beams, etc. So it's a rich variety of items off the shelves, making your life extremely easy. There are two ways of constructing concrete masonry walls. The first one is running bond, where every second block is an offset half a block. And then there's also stack bond. The good news here, the standard 429, I'm going to talk about later, is meant for architects to structurally design a masonry building, but architects love stack bond, and stack bond is not included. Stack bond falls outside the scope of 4229. If an architect wants to do that, he always needs an engineer to specify the design. The blocks are made of a fine aggregate concrete mix. That mix is then placed into the mold. After that, it comes out of the mold, it's heated for advanced accelerated curing. And then the blocks will be sitting outside on pallets, cubed and stored outside where the curing process continues. So the blocks should be pretty cured once they come to site. The strength is tested to Australian New Zealand standard 42456. The typical strength of the blocks is 12.5 MPa. However, if you build near the beach in corrosive zones, you would go up to 25 MPa. Standard is 12.5 MPa. Once you are familiar with these blocks, you can actually create stunning buildings. This is the famous architect Mario Botta, Swiss from Tessin. And you can see there are really no limitations to the design if you build with these small blocks. I always like to compare concrete masonry a bit to Lego for adults, because its main components are blocks and you put them together in a very simple fashion. They are rather small, so you can get them to sites with difficult access relatively easily. So the next one, standards providing guidance to masonry construction. There are three main standards. I always have to show this up front, since I will cite and show some extracts of these masonry standards. We have the permission from Standards New Zealand to do so. The first one is 4210, which is the standard for the builder and for the contractor. It talks about materials and workmanship, not just concrete masonry, but also clay and natural stone masonry. The next one then, 4229, is that standard we look into in more detail, the standard where we wouldn't need an engineer to structurally design that building. However, there's a limited scope, and if a building is more complex and more complicated and falls outside of the scope, then we need an engineer, and he would design to 4230. And this is something Enrique will talk about in the next hour. Other related standards, 3104 concrete specification, 3604 the timber standards has some concrete masonry foundation walls, and the loading standard. 4210, what does it contain? It shows you everything about mixing the mortar, mixing the grout, how you store your material and handle it on site, which are the preparations of the slab up front before you start laying the units, how you place and temporarily fix the reinforcement to ensure it stays in place when you fill the cells with grout, shrinkage control joints, grouting, cleaning out, which is very important. It also talks about hot and cold weather construction, which is above 25 and below 5 degrees. It talks about tolerances and chases. Another good news for engineers, chases are not allowed if you use 4229. If you want to do chases to hide your conduits, electrical or plumbing, whatsoever, then the architect has to ask an engineer. The only option for the architect is then, if he doesn't want to talk to an engineer, to hide it behind strapping and lining. Propping against wind forces, you can imagine the walls are pretty fragile when they're up for within the first 5, 6, 7 days when the mortar doesn't bond. So they have to be propped against wind forces. Also talks about masonry strength, how you achieve this with your mix, veneers, testing, and maintenance. So the next one here is 4229. That is a standard not requiring an engineer. However, for the observation on site, actually, you will still need an expert, either an engineer or a licensed building practitioner. You can design structurally, but not build without the observation of an expert. The 4229 is limited to 2.5 stories, maximum 600 square meter if it's a single story. Talks about site requirement, how you brace that building, how you design the foundations, what the slab on ground conditions have to be, how you design diaphragms, beams, lintels, and columns, shrinkage control, and is also limited to level 1 and 2, and not 3, 4, and 5 of 1170. There are appendices, one on retaining walls, which is always good for an engineer who wants to get a quick feel for the design of a retaining wall up to 2.40 meters, I think it is. There are also standalone cantilevered walls and a design example. This is in particular interesting for people who really want to get an understanding of 4229 because it shows step by step on a simple design how you design all these things, foundation, bracing, etc. So in the graphic, the limited scope, 600 square meter if single story, if 2 stories. And your lower is concrete masonry, and the top floor is timber framing, what we often see in Wellington, where we have sloped side. Then 350 is the maximum. If there is an attic here as well, so like this, then you would reduce the maximum size, footprint size, to 250 square meter. Actually, and the next one here, the last graphic I shows roughly the maximum what is possible. So 10 meter, that's the maximum. The maximum height from floor to floor, finished floor to finished floor, is 3 meter. Say 3 meter plus 3 meter is 6 meter, maybe 2 meter an attic, 8 meter, and then you are still allowed to have a foundation wall up to 2 meters. So this is roughly the maximum scope. The roof shall not be steeper than 45 degrees. 4230 then, so if it falls outside the scope of what we saw earlier, then the engineer uses 4230. And 4230 has everything about design requirements, how to comply with B2 as well, durability, and clause C, fire resistance, reinforcement, structural walls, beam, column joints, secondary structural elements, 6 appendices, one on pre-stressed masonry, on compressive strength, bolted connections, partially fill requirements, and specific design for small buildings, and also on veneer. That's 4230, but that's all I will say about 4230 in my part, and I leave it then to Enrique to go into more detail. So what I want to do now is show you how 4229 designs a foundation for a simple building. Firstly, there are 2 options. Either you can have a concrete foundation wall with a pad or a thickened slab edge. However, the steel requirement is the same. And also the width here, the 300 millimeter, would also be the same. I decide now for my example for the masonry floor, for the little pad. And to do that, I have a beautiful designed house here. Very simple house, 4 walls, 4 bracing lines, single story, 250 high, 250 gable. So to now design the footing, we have to know what are the loads on the footing. We have two different loads, the one coming from this area. This is the load we have to consider here is the wall from the stones, from the blocks, plus the load from the roof, which sits on top here, corrugated metal roof, let's say. On the gable end, however, we only consider the wall, but we also have the gable end here, which we have to add to the 2.50 m wall. We don't consider, 4229 doesn't consider any load from the roof on this wall. There are additional securities also always in the standard, so we don't need to do that. So what we have to do, what are the loads here? What are the loads there? And then again, 4229 keeps it simple. Whichever load is higher will govern for the entire building. Let's say if you have 15 kilonewton per meter here, maybe 18 kilonewton per meter here, then we would assume there would be also 18 kilonewton here. So the foundation is always governed by the more heavy load, by the higher load. So now what do we need to know? What type of blocks are we using? I'd say now we use the 200 millimeter blocks and then fully filled wall, high density. And the other thing we need to know is what are the loads from the roofs. That's all we need for the simple design. Yeah, if we have a two-story building, we then need to consider also dead and live loads from the slab, whichever that is, if it's a timber floor or concrete floor, so different loads, but we keep it simple. So there is a table in 4229, table 6.1, which gives you the density of these blocks. So we said we are using the denser blocks fully filled. This is just an extract. The table 6.1 has many more options, but I just copied the part we need here today. And the unit weight is 3.9 kilogram. But since there is no engineer involved, the authors of the standard thought, hey, we just chuck in a bit more. So we have to consider the factored unit weight, 4.6 kilonewton per square meter. But our building is taller than 1 meter, it's 2.50 meters. So we multiply that 4.6 with 2.50 meters, which gives us 11.5 kilonewton per linear meter sitting on the foundations from the wall on the long side of the building. The gable end is then a little bit different, but you engineers, you know how to calculate the area or the average height of a triangle. So you just divide the highest point, the 2.50 meters, by 2, which is 1.25 meters. So again, we have to add to the 11.5 kilonewton 4.6 times 1.25, which is this one here. And that results in 5.275. So in other words, the gable end is 17.5 kilonewton per meter. So on that gable end, the load coming down on every linear meter of the footing is 17.25 kilonewton. But now we have to go back to the long side of the wall because we have to add the weight from the roof and have to compare whichever is higher. So to do that, it's extremely simple again. We don't need to calculate anything. We just go into that figure 6.1 where loads are graphically given. So there are 4 options. The first line here is for assuming we have a corrugated light roof, corrugated metal light roof. The next line assumes it's a concrete tile roof. This one would be a light roof with an attic, and this is a heavy roof with an attic. Super simple. So we only have to remember what the width was of our building, and I think it was spanning 7.80 meters. We would just draw a vertical line, grab the figure where those 2 lines meet, and just assume something like 4.2. It doesn't matter. It doesn't make a difference to the design of the footing if we would have picked 4 or 4.5. It would still be the same design. As you will see later, there are heaps of tolerances in the design of foundations for 4229. So 4.2 is the additional load per meter on the footing. We add this to our previously determined 11.5, and that makes 15.7. Quickly compare this with the gable wall, which is 17.25. So this load governs, and we assume now that our footing has to take 17.25 kilonewton per meter. Once we know that information, we go into this table, which gives us 5 options for foundations, depending on the load per meter. So this one goes up to 40 kilonewton per meter. This one goes even up to 100 kilonewton per meter, which is quite a lot already. Yeah, obviously this one here relates to this one, 17.25. So this is the design for our footing. Simple as that. We have already now achieved to design the footing for the masonry building, 200 tall, 300 wide, 2 D12s horizontally, and stirrups, round steel, 6 mm each, 600 mm. So that's it. The heavy one, that would be this one here, which is very bulky, lots of steel, very thick, up to 100 kilonewton per meter. So this is how you design a foundation for a masonry building when you use 4229. Slab on grade, just some words, but I think you're very familiar with that. You excavate a bit, then you place a sand base, which protects the waterproof membrane underneath from injury, from being damaged by any sharp stones in the soil. Then you place your reinforcement, the 500E mesh on chairs to prevent it from falling down. When you pour the concrete, and you keep it moist for at least, let's say, 7 days to guarantee, to ensure there is a homogeneous curing. And the minimum strength will be 17.5 MPa. I know it's mostly rather 20 MPa, 17.5 MPa. And yes, since Christchurch, you're very familiar with that, we need at least a 500E mesh in the slab. I'll quickly show you, if we would have a 2-story building, we would have to consider firstly the 2 kilonewton per square meter for live loads taken from 1170 for residential, and similar like the assessments of the loads from the roof. We have a table here for suspended floors. For timber floor, that's not heavy. You would only have to add 0.5 kilonewton per square meter. If it's a heavyweight concrete, you would have to add 4.5 kilonewton per square meter. So that's relatively straightforward. That's the way how you would design footings. I'm going to talk about walls in general now, to remind you the 4 things we need: the block, the mortar, the reinforcement, and then the grout. This is obviously an engineered wall. If it would be 4229, we would only have every 4th cell, something like this, but this one is heavily reinforced. Not sure what this is for, but it's a heavily engineered wall. And the mortar strength and the block strength, both 12.5. It is important to tool the joints, even if you apply a weather tightness system like an EIFS later on. They always need to be tooled to ensure it's compressed and it's performing as it should. The thickness of the mortar should always cover the entire face shell thickness. And yeah, the grout then is the strongest part because that bonds the rebar and the blocks together. As you can see, also on this one here, there's an upside down block. That is the first row here to create better bond with the slab. And then we have clean out openings. And here we clean out all the debris from the 12.5 MPa mortar. You can imagine it's squeezed. You always have some mortar projecting here and also falling down. And if it's projecting, that would potentially compromise the grout. The grout is 70.5 and the mortar only 12.5. So we want a really clean surface here to ensure that the whole cavity is homogeneously filled with the 70.5 mortar. This is the opening where also the building inspector comes and has a look if everything is clean before you fill the grout into the void. This shows the, yeah, it's good to show where reinforcement is required for 4229 buildings. D16 beneath, and here this can be D12s or D16s on top for the lintel, or maybe it's already the bond beam. On the sides we need reinforcement. Further we need reinforcement at all corners. We also need reinforcement to the left and right of shrinkage control joints. There is a there's a maximum allowance for an opening where we don't need reinforcement. That applies to bracing walls as well. We talk about bracing later. For a bracing panel, you have an allowance of a 400 by 400 maximum opening. Either side of shrinkage control joints, we need vertical bars, and horizontal bars shall be provided below and above the wall. And if it's partially filled, we need one at the top of the wall, so the maximum is 2,800. If it's a fully filled wall, we need reinforcement, each horizontal reinforcement, each 1.20 meters. The load capacity of these walls, if we stick with partially fill, 200 series, 1 meter, for example, that's almost 100 kilonewton. I just see there's possibly a mistake here. That should be 248. To talk to the 4229 committee. So this is the table which gives you the vertical load capacity of your walls. Next one, grouting. Grout is fine aggregate concrete, 70.5 MPa. The grout will be stronger in corrosive zones as well as also the blocks. The blocks will be 25 and the grout will be 25. Most commonly, you would add an expensive admixture, and similar, like with self-compacting concretes, these types of concretes are not measured in slump but in spread. And there are 4 methods for the grouting, 4 methods available. That again is described in 4210, as you can imagine. So high lift grouting with and one without expensive admixtures, low lift grouting, high lift grouting. They vary in the height in one go you can achieve. So the most common one is the top one here. This is the one most contractors go for, which is pretty straightforward. Firstly, as I mentioned, they have to be cleaned. But what that means is 3.60 meters, you still have to go left and right. And so you always have to go further once 1.20 meters is achieved and then come back. It can be one go, but you still have to let it sit a bit. That means the semi-continuous operation. So 1.20 meters, come back for 2.40 meters, and then come up at 3.60 meters. Once that is done, you consolidate and compact the concrete and get a bit of the air out of that grout. And since you have an expensive admixture, you have to trowel the top down once it's all in. This is so much about grouting. Then shrinkage. You as an engineer would be very familiar with shrinkage. So the concrete is losing water, so it will shrink in volume. The water is needed for the hydration process to trigger the gluing properties of the cement, to bind the blocks, the aggregate together, form solid stone. But so in other words, we can't prevent the concrete from cracking. But what we can do is tell the concrete where to crack. And this we do by shrinkage control joints. Coming back, obviously we don't have to consider the blocks. The blocks are fully cured, but we have to consider the grout. That's why we place shrinkage control joint in the grout. So there is a filler strip here where the horizontal reinforcement is placed to prevent any concrete getting through. The standard joint would see the reinforcement stopping, then lapping by a block length, 400 millimeter here. However, the one side needs to be debonded. So there needs to be movement. And you achieve this either by greasing the steel or by wrapping it with TPM or so, but ensure that there's still movement possible here. This is a standard joint, let's say at a 1.20 meter level. If you would be at a bond beam, then reinforcement would actually go through, which I think is, so this is a standard, let's say 1.20 meter joint. But yeah, so if it's a bond beam, you can see here the reinforcement is going through. If it's a standard joint, the reinforcement stops, goes down about 1 meter, maybe about 200 millimeter, and here as well. And then there would be the debonded bit of that lap beam bar, and then there's the other bit sitting in the concrete. You see the vertical reinforcement just here in the last cell of the block, and that will tie in and lap in then as well into the bond beam. Hello. So shrinkage control joints in the average every 6 meters. We have to have a shrinkage control joints coming to corners. Yeah, that would be 600 millimeter, as we can see here. Or if you want to have a symmetry, then you can go to 3 meter 20 by 3 meter 20. But you could also go here to, let's say, 4 meter and maybe 1 meter 80 here. So you can squeeze and balance that out, but no more, no less than 600 millimeter here at the corner, and then you stretch it. You have always a control joint where the direction changes of the slab of the wall, if it's a U or T junction. Also, when the wall height exceeds 600 millimeter, for example, your ground floor is taller, is larger, the footprint than the upper floor. Maybe there's a deck, a walkable deck on top of that larger ground floor, and the wall goes higher up than where the building continues. There you need a control joint. Also, if you have your wall thickness changing, you may want to have a 250 block to retain earth, and maybe there's along the line of the wall there is no more soil to retain, so you just swap to 200 millimeters, or you need to address this with a control joint as well. Yep. Tolerances. I don't want to go too much into detail. There's a table again in 4210, standard for the builder. Deviation from original position 550 millimeter. Vertical alignment over 1 story, that's 10 millimeter. Total vertical alignment for the complete building height, that's 20 millimeter. Vertical alignment between, let's say, the first floor walls to the ground floor walls, that's 5 millimeter. Mortar joint thickness, I think it's quite generous. So your mortar joint could be 7 millimeter or 30 millimeter. So you make sure that you have a good builder, because if you have a 7 millimeter and a 30 millimeter joint, that would not really look good. And yeah, so, but it's still allowed. So that's the maximum minimum tolerance. The full tolerance list is actually here. This is how it should be, perfectly aligned. In addition, they have used a beautiful honed concrete where the smaller aggregate is exposed. And I think that looks really stunning. Yeah, otherwise, if you don't stick with the tolerances, you have a masonry building like this here. However, in everything which seems to be bad, there's always something good, because this building is generating heaps of money from tourists, so it's not all bad. Beams, lintels, and diaphragms. So I will start with bond beams. They sit on top of every wall. There's no concrete masonry wall without a bond beam. We need this to stabilize the top of the wall. There are 3 options, B1, B2, and B3 bond beams. The digit just describes the amount of horizontal rebar. A B2 bond beam sits on top of the wall, and a B3 would sit at intermediate level, which is good to see here. So this is a B3 at intermediate level. That would be the same if it would be a full story, a full second floor. And we have the raking bond beam would be a B2. However, if you have a diaphragm in this level, which is often the case, then you could go down to a B1. Yeah. Then also how the labs function, how the measurements for the labs, that's all given in 4229. Lapping at corners and also at T junctions. And this table shows the maximum distance of your bond beam walls when you want to use them for bracing, or if it's a bracing line. Then the maximum distance let's say in Wellington, where I am now, using the 200 blocks, then the maximum distance would be only 6 meter 40. You may remember that our building spans already 7 meter 80. So there are options then. 4229 allows various options. Either you use simply the bond beam walls. If you want to go further than these limitations here, then you would have to use the diaphragm method. The diaphragm method is described then in the chapter on diaphragms, and that says you can go up to 16 meters. So 16 meters is the maximum. This sentence also says you could use a roof diaphragm. A roof diaphragm, if your roof is not steeper than 25 degrees. If it's 45 degrees, then you have to use a ceiling diaphragm, a horizontal diaphragm at ceiling level. Yeah, and you as engineers perfectly know what a diaphragm does. So it just protects the building and stiffens the building in this area. And how is a diaphragm connected? If it's a roof diaphragm, 25 degrees or less, then you have M12 bolts sitting here and also M12 bolts here. The connection is then always protected with a DPC to avoid any moisture from the concrete or from the grout still curing getting into the timber. If you have a suspended floor, if it's a timber floor, again, you have the bolts here connected to the timber structure of that floor. Or if you have a lightweight roof on top, then you would also place a connection on top of that wall. If you have a suspended floor of concrete, when it is within the concrete, it looks like this. You always have the rebar connecting from the vertical bar to the mesh, and that's here the case as well. This is the lightweight solution, and there's also a veneer solution on top. So this is just the structural solution. Obviously, for weather tightness, you still have to do something here. This can work like this also for weather tightness if you have, just have to be careful about draining out here. You don't want to spoil the facade with any water running down the wall. Anyway, structurally, those options are provided to connect a diaphragm from a suspended floor to your concrete masonry building. Again, these are just extracts. 4229 is much more comprehensive. It shows you many more options. There are openings allowed in diaphragms. So 40% of the total diaphragm dimension if it's perfectly in the middle. 40% does not mean the 40% of the area. Let's assume this is 10 meter by 10 meter. So the diaphragm would be 100 square meter. It's not that your opening can be 40 square meter. No, the 40%, they refer to the length. So 10 meter, then this would be 4 meter, let's say, and this would be 4 meters. So the area is not 40 square meter, but 16 square meter. And if it's outside the middle, if it's somewhere here, maybe you have stairs going up and down here, then it would be actually just 20%. So 2 meter and 2 meter, that's actually just 4 square meter. But that's allowed. Otherwise, again, you would need an engineer to design for that diaphragm opening. So that was the diaphragm and the bond beams. Now lintels. And again, I will show you now on example of these simple house, how we design a lintel for that simple house. There are ready-made options in tables in 4229. There are 190 millimeter tall lintels and 390 millimeter tall lintels. And there are tables for these. So you decide as an architect, do you want to use 190? Check in the table, is it sufficient? Otherwise, I pick 390. So again, for the simple building, we only need to know the loads from the roof. And you may remember how that worked. We just looked at figure 6.1, picked the number here, 4.2 kilonewton per meter. That's the load sitting on every linear meter of our lintel. And we have to now also quickly look at the design. The maximum lintel spans, I'll just tell you now, I'm the architect, 2.60 meters. This is the door to the deck, the door to the terrace. There's a sliding door, huge door. 2.60 meters, that's the maximum span for the lintel of our building. And once we know that, we go into table 11.5. Again, there are many more tables. This one is for the 390 millimeter tall and for the 20 series. So there are also tables for the 190 millimeter tall and the 20 and the 50 and the 25 series. But we are right at the right place here if we look into this table. So the spans are given along this row. So 2.60 meters, that's here. The load on the lintel is given along here. We may sometimes have to interpolate, but actually it's not necessary because we have the load 2 meters, 4.2 kilonewton per meter. We could assume it's 6. So we are here, and everything in this gray area would be the same. We know the measurements: 390 millimeter tall, 190 millimeter wide, and the reinforcement here would be 2D12s with R6 stirrups, each 200 millimeter. If you come to heavier loads, let's say, let's pick that one here, 18, and you want to span 3 meters, then you would have to pick this one. The difference is the amount of stirrups is increasing. But if you go to 4.20 meters, then the amount of the horizontal bar would increase from 2 to 40, 16 actually. This is how we design a lintel by use of 4229. So I think it's also pretty straightforward. The next one now, bracing. So how do we brace? Masonry building. So you all know we need to brace against wind and earthquake forces. We can account every panel which is 800 millimeter or larger in length. The maximum height is 3 meters. We brace every story by itself. And as I mentioned earlier, the maximum allowance of an opening is 400 by 400. You all know what bracing units are. 1 bracing unit is 5 kilo, 200 bracing units, a ton. And firstly, we have to identify the bracing demand for our building if it's built and located in this location on a specific soil type. And then we do the bracing design. Then we check if our design fulfills the bracing demand. Bracing line is external to parallel to external walls, shall be within 1 meter of bracing wall. So let's assume this is our bracing line here. It would be then okay to have the wall here and maybe a bay window 2 meter, 2 meter back. So maybe 4 meter, 2 meter, 2 meter. Then this is still considered as one bracing line as long as this distance is not more than 1 meter apart. But you remember our building needs a diaphragm because we're exceeding these bond beam walls distances from that table in 10.1. So we need a diaphragm. But if we use a diaphragm, then that means every of the single walls, so this is my footprint now, every of our 4 walls would need at least 60% of the total. So say we may figure out that the bracing demand for the whole building, 100 square meter, whatever it is, maybe 3,000 bracing units in total. Then every bracing line, every wall would have to provide already 1,800 bracing units, so 60% of the total. There's one exception if one wall, let's say this one has already 100, and maybe this one is already 100%, so this one provides already 3,000, and this provides 3,000 as well, then those could go with 30%. So those could go with 900 bracing units then. However, the general rule of thumb, always consider every bracing line has to provide at least 60% of the total if you use a diaphragm. That's important. So how do we get the number now? How do we find out what the bracing demand on this simple building is? So we have to know where it's built, which earthquake zone, on what type of soil we built the building, how many floors, dead and live loads, and the footprint size. These are the 6 parameters we need to determine the bracing demand. Here's all the information. Okay, it's located in Wellington, which is earthquake zone 3. We use 200 blocks fully filled. We have a light roof and we build on subsoil class C. Once we know that, yeah, so here are the earthquake zones. Wellington is here, number 3. Auckland is 1. Christchurch is 2. We built in Wellington, earthquake zone 3. Now we go into this table which holds a lot of information. Again, this is only an extract. This table 4.3 is much larger, has single stories, 2 stories without attic. But this one will do. Again, we look into the table and identify, aha, this is our building with light roof. So we are building in Wellington, zone 3. We have 20 series walls. That's 28 bracing units per square meter so far. But since we have fully filled walls, not partially filled, we have to add a bit more because it adds more weight. So we have to multiply that with 1.4. Instead of 28, we almost get 40 bracing units per square meter of our building footprint size. But there's another thing we can consider now, the subsoil class. We said we build on ground C. This table and these values are written for weaker soil, for softer soils. And since we are building on an average soil, we can multiply the number of 39 with a figure lower than 1. So we can reduce our bracing units. If you would build on rock, then you can almost reduce it to about 3/5. Okay, this is the number we figured out. Lightweight roof, 20 series wall fully filled. That's almost 40, but we build on a bit better soil than these soft stuff here. So we can deduct a bit of the bracing units again, and we come to the conclusion the bracing demand for our building built in Wellington on that subsoil, that's 31 bracing units per square meter. Now we only have to know what the footprint size is of our building. You remember it was 12.80 by 8 meter. That accumulates to 102 square meter times 31 bracing units. So that's a bit more than 3,000. That's exactly 3,174 bracing units. So now we know what the building has to achieve. The building has to brace for 3,174 bracing units to withstand earthquakes in zone 3. We only have to compare now if maybe the wind demand is higher. So we have 2 directions, across the ridge and along the ridge. So once again, we see our building is here. The total height, including the gable end, that's 250 plus 250 is 2.5 meter. The roof above eaves, that's the gable, that's 2.4, not given here, so we interpolate. For the across ridge direction, we need 88. So that's 88 times 8 meter the width of the building. That's just 704. And in the other direction, that's again 88. Yeah, sits in the middle. That's 1126. That's way less than this figure. The same like with footings, the higher demand governs. So we forget about wind and use the earthquake demand. It could be different if you build in Auckland. Maybe the bracing units here are less, maybe just 1,000, and suddenly we have 1,126. Then we could still check in which zone, wind zone, we build. In the notes, you can see this one here is written for extra high wind zone. And again, same like with the subsoil class, if we build in a lower wind area, maybe just a very high wind zone, we can also reduce that figure. So that would bring us below 1,000 actually. So this is how you check wind and earthquake demand. The earthquake demand is mostly governing in most areas. Yep. So now we know we need our building has to provide 3,174 bracing units. We now have to check our 4 panels, what their bracing capacity is. So this one is the first panel I'm going to look at. So we have a construction joint here, construction joint there, and the bracing panel only extends to the construction joints and then to the openings. So unlike with timber buildings, let's say 3604, timber buildings, we have studs everywhere, And here we have to brace the spaces between the studs, which is not necessary for masonry because the block itself is already braced, nothing happens. This is why we only brace the openings. Yeah. And so here's just a bracing panel, which would actually provide many more bracing units than if the panel would extend down here. So this panel provides possibly 1.5 times the bracing units the entire panel would give us. Simply because if it's a standing panel, yeah, it can easily tilt over much more easy than a lying panel. So that's much better for bracing. So this is how 4229 works. We only brace between the openings and the construction joints. So now we look at these panels. This panel, how many bracing units does this panel provide? Very straightforward. This panel is 240 by 240, and this panel is 140 by 2 meter. Again, we just go into a table. Yeah, 240 long, 240 hay. So the first of the 4 panels provides us 820. And we have another one of 820, that's already 1640. And then we have to look at the other panel, which is 1 meter 40 by 2 meter. We interpolate between those two figures. That's roughly 400. So 1600 plus 400 plus 400 is roughly 2400 bracing units. And this is how I line them up. Yeah, so this is the bracing line A, you know, the little gable wall with these 4 panels. One here, one there, the 2 smaller ones here. 800, 400, 400, 800. So we achieve 2,436 bracing units alone in this bracing line A. So we only check if this is exceeding the 60%. You remember we use a diaphragm. Every bracing line has to achieve at least 60% of that total. So 60% of that total, that is 1900. So this is way above. This bracing line is good. So it's perfectly braced, and now we would just simply go back to our sketch and just pick the next, in this case, 4 panels. We have 5 panels here, and see how they perform, how they come out. So this is how bracing works for 4229 buildings. Pretty straightforward. And once again, you do it for story by story. My last section. We talked about all these standards. There's also material given from brands and standard New Zealand. But what I want to point out is on our webpage, concretenewzealand.org, under the masonry sector group, there is heaps of information for you guys, which is all related to 4229 and 4230, but has more detail. So we have written a very comprehensive book, the New Zealand Concrete Masonry Manual, talks about properties of concrete, construction details, reinforced masonry. We have just updated, actually in this section, a retaining walls. Then we, yeah, this is the updated section. So due to the earthquakes, there was a recommendation from MB, Geotech, a recommendation, and all those findings we just chucked into this chapter 6.1, retaining walls. So soil parameters were now more generalized. We applied various surcharges, a little bit more accurate. And yeah, all the changes reflect the guidance from the earthquake findings. Once again, CPO1, we provide wall types, weather tightness systems, flashings, roof, foundations, construction moisture, and detailed drawings as well. They are very comprehensive. They always refer back to the text. So it's a good stuff, also free download. We have a trompe wall guide, you know, for passive solar design. We also have written a basement design guide. Since CPO1, the weather tightness code is only for above ground walls, not for in-ground. So we have provided a basement design guide. And yeah, so I recommend that you can have a look here, download these guides. Also download 4229, which is a free download now as well since a couple of months. I think I'm through here, and thank you so much for your attention. Over to Enrique.
Okay, so hopefully you all can see my screen. Have the PowerPoint up there. So my name, thank you, Jeff. So my name is Enrique del Rey Castillo. I'm a lecturer at the University of Auckland, and I am also a Concrete New Zealand Fellow. I do research and teaching on concrete structures and seismic behavior of concrete, how to strengthen concrete structures, mostly with FRP. So this is part of what I teach. I think actually Jaffer was my student years ago when I was teaching this course. If you need to contact me, there are not many Enrique del Rey Castillo in New Zealand, so just Google it, you can find me easily. But I have there my email address, and you can also find me on LinkedIn if you need anything. My presentation is more engineering focused, so it's more numbers, it's more design methods based on the principles of how to design beams, walls, and columns. So it's not so focused on the actual practice because I don't have the time, I have only 1 hour. So I may have to run a little bit. Let's see how it goes. Right, so we have 3 types of masonry, but like Ralf was saying, type B is the most commonly used. So I'm going to assume that we are using type B all the time. So the strength is 12 MPa, the modulus of elasticity is 12 GPa, and the strain is 0.03. The strength reduction factors, same as 3101, very, very similar. We are going to be using mainly flexure with axial tension for walls and columns, and shear. So the reduction factors are 85 and 75, nothing new here. Now, 4230 gives us the option to design for elastic, nominally ductile, limited ductile, and ductile structures with the ductility from 1 all the way to 4. Similar to other standards like 3101, the section chapter number 0.3 is for elastic and nominally ductile structures. So if we are in chapter 8, for example, 8.3 will be how to design these 2 types of structures. If we want to design for limited ductile and ductile structures, we can do that. The standard allows to do that, and then we go to the section number 4. But it's usually preferred to stick to nominally ductile structures. Why is this? Well, it's simpler design. We don't need to design the seismic detailing, and it's usually at the end of the day is more cost effective because we don't need seismic detailing. We don't need so much steel. So it's usually preferred to use nominally ductile structures. That means that during this hour, I'm going to be focused on nominally ductile structures, sticking to the chapter 3 or the section 0.3 and ignoring the section 0.4. But if we want, we can use either 10.2.3 for the moment capacity or 10.3.3 for the moment capacity. And these equations are explained in more detail in the masonry manual, the same document that Ralf was referring to at the end of his presentation. There is a lot of information in there, word examples, more details, commentary. So I strongly recommend that if you are designing buildings with concrete masonry, you download this file. It's free to download and have a good look at it. Right. There is, before I enter into how to design beams, walls, and columns, there is a limitation in maximum rebar size. This is coming from the masonry manual. So if we have walls and beams, depends on the yield strength of the steel and the block size, we can use up to certain limit, up to certain size of rebar. And for columns, we have the number of bars and the diameter. So just keep that in mind, and we will need to do that check during the design. I'm going to start with beams, just because it's the simplest. So it's chapter 8, and we are going to be focusing on 8.3, the nominally ductile, the nominally ductile structures and elastic structures. There is a limit in the diameter of the bar, is the smallest of 1/4 of the smallest dimension of grout space. So that's the void inside the block, or 1/8 the smallest beam dimension, that's the external dimension. Then we have maximum reinforcement area of steel, depending on the area of grout and the strength of the steel. And finally, we have a reinforcement ratio, lower and upper limits, in those two clauses in there. And the lower limit depends on the steel, and it's just a percentage. The upper limit depends on PB, which is the ratio of longitudinal reinforcement that will produce balanced strain conditions if we don't have axial load. Right, so the way I teach to my students is through examples. I do a lot of word examples. And this is basically what I'm doing today. I have one example for a beam, and it's really simple. So you are engineers, and I don't see any complexity or any difficulty with you to follow this example. Then we have a wall example, and I will do one example and give you guys another 2 examples so you have more word examples. But I don't have time to do the 3 of them. And finally, we have a column at the end. So in this example, we're going to design a beam using 15 block series with 300 steel, and my M star, my action, is 6 kilonewton meters. Now, I'm not telling you the span of the beam, because I'm just going to do a section analysis. But if we do have the span, if we do know the span, then we have these limitations on the dimension of the beam. Now, because it's simply a section analysis, we have the section in here is 200 high, 190 plus 10 for the mortar. The steel is in the middle. We have strain compatibility, so it's linear, strain in the concrete, the neutral axis depth, the strain in the steel at yield, and then we have the compression block, the compression force coming from the block, and the tension force coming from the steel. I'm sure you know this for years now, but it's basically the basics of any design, right? We can start with D20, for example. We can calculate the tension force. It's just the area times Fy. We have 94 kilonewtons. For this section to be in equilibrium, we need to have the compression force equals to the tension force. So my 94 coming from the tension is equal to that block in there, which is 85 F prime C, or F prime M in this case, times A, which is 85% of C, the width of the beam, and F prime M. From there, we can extract C, and we get 77.6 kilonewtons. Then once we have that C, we can take moments. I've taken moments in the neutral axis, but obviously you can take it anywhere. So my compression force times the distance plus my tension force times the distance. We have the numbers in there, and it gives us 6.3 kilonewton meters. We multiply that by the strength reduction factor, is 5.4, which is smaller than 6. So it's not enough. Now we can try a D25 or HD20. In both cases, we have 6 kilonewton meters, which is just the same as my M star. But we need to check the size. So the limit for us is a D16. So it's too big. We cannot design the beam like this. We just need to change the longitudinal reinforcement. We need to change the size of the beam, and use a 390 block instead of 190 block. And that's all. As simple as that. It's just a beam with a moment on top coming from the UDL. Simple. Now walls. This is chapter 7.3. So if you remember, the beams was chapter 8.3. And the beams was 8.3 and the walls is 7.3. But I started with the beams because I think it's simpler. So I go from simple to more complex. There are several checks that we need to do for the walls. The first one is dimensional limitation to make sure that the wall is stable. So the minimum thickness, the thickness of the wall, the minimum thickness of the wall is either 140 millimeters or 5% of ln. Ln is not the length of the wall. Ln is the distance between the bars. So the bars at the end of the wall, the distance between those. And then we need to check the minimum reinforcement ratio. If we have running bond, is the sum of horizontal and vertical larger than 0.2%. If it's stack bond, it depends on the importance level of the building, from 0.07 to 0.25. Now, how we calculate or how we make sure that our capacity is larger than the demand. This is the same as for other standards like 3101. The strength reduction factor times the capacity has to be larger than my demand, my end staff. Now we calculate my capacity with this equation there, based on the compressive strength of the masonry, which is 12 for our simplification, the gross area of the wall, and then a function of the distance between the bars and the width of the wall. But we need to design the wall as a column if the distance between the bars is 790 millimeters or less, and at the same time, my axial load is more than 10%. Both at the same time, not one or the other. Then we have the moment capacity, same principle, the capacity times the strength reduction factor larger than my action, and the same with the shear, but we need to calculate also the stress. So small v is the stress, capital V is the force. Right. Now, how do we design walls? I'm going to start with in-plane design, and then I will do out-of-plane design. With the in-plane design, for flexible is based on first principles. So we have the bars there, we have the axial load coming from the upper floors, and the moment coming from the earthquake. Then we have strain compatibilities, straight, and then this is based on bilinear behavior. So we have up to yield and then horizontal. If we wanted to consider strain hardening, it would be more like something like this, right? And then we have the forces. Summary of vertical forces equals to 0 to be in equilibrium. The only issue with this is because we have so many bars, it's going to be quite time consuming if we have to guess the C and iterate until the equilibrium is satisfied. So there is a little trick that I will explain later when I do the example, based on the moment coming from the axial load and the moment coming from the steel. I will explain in more detail later. Then the shear design is based on, or it depends on whether we have fully grouted wall or partially grouted wall, because if it's fully grouted wall, the whole gross section of the wall is taking the shear or is contributing to the resistance of the shear. However, if we have partially grouted a wall where only one every 3 or 4 holes is grouted, then only the shells of the wall, that thin one there and that thin one there, are actually contributing to the shear capacity of the wall. So we need to take that into account by defining the width of the wall as the fully thickness of the wall, or as the thickness of the wall minus the width of the grouting hole. So if we have 190 thick and then each shell is 30, that's the thickness of the effective thickness that we're going to be using, 30 and 30, 60. Then we calculate the stress based on the contribution of the masonry, contribution of the axial load, contribution of the steel, in case we want to put the steel in this direction, or we can. And we calculate the capacity. So first, the contribution of the masonry, or the strength provided by the masonry. It depends on these two factors, C1 and C2, and the stress Bm, not M, but Bm. In our case, because we have 12 MPa concrete, our VBM is 0.7. That's simpler. Now C1 depends on this factor, which is the ratio of longitudinal steel and post-tension longitudinal steel in the tensile zone. So that's why it needs a specific nomenclature, divided by the gross area. And then C2, it depends on the height divided by the wall length. This is the whole length, not the distance between the bars. So whether it's smaller than 0.25, between 0.25 and 1, or larger than 1. Then the strength provided by the axial load. We can calculate that with that equation in there, based on the load, the area, the gross area, and the tangent of alpha, alpha being that angle there. If we have single bending, the load is in the middle. If we have double bending, the load is on the opposite side, on one of the edges. Now there is a limitation on how much axial load we can have, 10%, and a limitation on how much the axial load can actually contribute. And finally, the shear provided by the reinforcement. This is very similar to normal concrete or cast in situ or precast concrete. 80% of the area of the steel times the yield strength of the steel divided by the width times the spacing. We have a minimum area of steel that we have to comply with, and a maximum spacing, half the width of the wall. But this is relatively simple, similar to what you guys might be used to. And that brings us to out of plane design. So the flexural design also based on first principle. If we are doing retaining walls, which is one of the most common uses of concrete masonry walls, then we usually do it per meter, because we may have a 20 meters long wall or 10 meters long wall, so it's simpler. The only little detail that we need to consider in here is if we have a partially grouted wall and the neutral axis depth is larger than the shell of the wall, then we need to determine the area as if it was a T-beam, because the area then becomes like this. We may need to do some extra calculations in there just to calculate that area there. It might be better to just fully grout everything, and then we don't have that problem. So we need to be very careful in calculating where the C falls, where the compression zone falls, and take that into consideration later on. Now the shear design is a little bit more complicated. On one hand, because we have more options, we can have running bond fully grouted or running bond partially grouted, and we can have a stack bond fully grouted and stack bond partially grouted. So this is a little bit more complicated. We have more options for the effective width of the wall. On the other hand, it's simpler because typically we cannot have shear reinforcement. So we calculate the contribution of the masonry. It has to be always smaller. There's a limit on how much contribution we can have. In our case, we have type B, sorry. So this is our limitation for BM. And that's all. So as I said, on one hand, it's more complicated because we have 4 cases. On the other hand, it's simpler because we don't have to take into account the axial load and the steel. Right, so I'm gonna do this example now. Maybe some of you have seen it already because it's an example commonly used at Auckland. So if you studied in Auckland in the last few years, you probably have seen this. Maybe you don't remember it, that's another story. Basically, we are designing a retaining tank, water tank. And we are using 4 concrete block walls at the bottom. So one here, one there, another one behind there, another one behind there. We are going to use series 15 blocks with the same concrete, 12 MPa, and steel 300. I'm giving you the thickness of the shell. So that's 30 and that's 30. And I'm giving you the loads, 104 horizontal load, 400 vertical load, and we have these dimensions. 1200 millimeters, that's the length of the wall, and 1400 is the length, and 1200 is the height. And we are going to design the in-plane moment and the in-plane shear. I am ignoring the out-of-plane capacity of that wall if the load is coming in that direction. And I am assuming that only that wall and that wall are taking that load. Right, so let me play around with my screen. So you should see now split screen. Left half I'm going to do the grading, and right half I have my PowerPoint. Now my handwriting is terrible. I'm sorry for that. I think I'm a little bit too old to change that. I try to write slowly and as well as I can. If you don't understand something, you can type it in the chat and I will come back and change it. Okay. All right. So first, I'm going to do a brief sketch of my wall. This is my wall. The total distance is 1400 millimeters. And we are going to try to do partially grouted first, just for the sake of it. We're going to try and see what happens. So we're going to have one bar there, there, and there. So we have 4 bars and 4 grouted cells and 3 that are going to be sitting empty. And I'm going to say that we have 100 millimeters there. So that is 1200. So basically we have my length of the wall 1400 millimeters. My LN is 1200 millimeters. And then we have the thickness, which is equal to 140 millimeters from that example on the right-hand side. But my effective thickness, or my effective width, is actually 2 times the shell, 30 plus 30 millimeters, because we have partially grouted wall. And finally, the height of the wall, which is 1200 millimeters. So we start with the stability check. Basically, I'm gonna go here back so we can follow the slides here. So basically my thickness has to be larger than either 140 millimeters or 0.05 ln, and this is equal to 60 millimeters. So my B is larger than, my B is equal to T, which is 140 millimeters. So we are good. Now we are going to do the axial check. My N star is equal to 400, my total axial load divided by 4 walls. This is equal to 100 kilonewtons per wall. We are going to design 1 wall and then multiply it by 4. And then we have our NN. It's equal to 0.5. Let me move this down to there. And then we have FM times the cross area times 1 minus LN over 40 times B. Square. Like this. So this is equal to 0.5 times 12 times 1400 times 140, and then multiply by 1, 1200 divided by 40 times 60 square. And this is equal to 822. This is larger than N star. I'm not even bothering with the strength reduction factor because it's so high. We cannot check the minimum reinforcement. We will have to do that at the very end because we don't know how much steel we have. So basically what we are going to do now is design the moment capacity. So we calculate my M star, which is V times H divided by 2, because we have 2 walls taking that load. So it's 104 times 2.5 divided by 2, and that's 130 kilonewton meters for each of the 2 walls parallel to the load. So now we calculate, or we establish that the strength reduction factor times the capacity has to be larger than my action. So my moment has to be larger than my M star divided by the strength reduction factor. This is 130 divided by 85. So that's 153. And just as a reminder, my N is equal to 100 divided by 85, 180. Now, and this is the trick that I was mentioning before. We are going to split the moment in between the moment coming from the axial load and the moment coming from the steel, which is capacity, moment capacity. It's a 4 steps process. So the first step is to calculate A1. This is the A coming from the axial load. Then point 2 is estimate A2, which is the A from the steel by similar triangles. We will see that. Point 3 is with the moment coming from the steel that we can calculate because we have the A from the steel. We estimate, or we propose or try steel content. And then 4, we check if using A, which is A1 from the axial load and A2 from the steel, is giving us Mn larger than M star divided by the reduction factor. Right. So now point 1, we have our axial load. It's N118, I just calculated before. And now our compression force is the A1 times 0.85, the compression force of the masonry, times the thickness of the wall. And this has to be 118 kilonewtons, equilibrium. From here, we obtain A1, which is 118 times 1,000 divided by 85, 12, 140, and we get 82.6 millimeters. Now, again, we have to be careful here because we are doing partially grouted walls. So this hole is filled. So basically, if my C, my A was going to be larger than that distance, then we will have to calculate that area in there. But because my A is only 82.5.6, which is smaller than that, is somewhere in here, we don't need to do that because it's going to be a square or a rectangle. Right, so now once we have that A, we can calculate the moment coming from the axial load, which is my C, my N, times the distance, 1.4 over 2, A1 over 2, and this is 77.7 kilonewton meters. Now we can calculate my MS because it has to be Mn minus the moment coming from the axial load. So this is 75.3 kilonewton meters. Now we can estimate step 2. We can estimate A2 by similar triangles. So we can say is equal to A1 multiplied by the ratio between the moment coming from the steel and the moment coming from the axial load. And this is equal to 80 millimeters. And now point 3, we calculate MS. This is equal to the area of longitudinal steel times the yield strength of the steel times the length of the wall over 2, basically the distance, A2 over 2. From here we obtain AB, which is, it has to be higher than 435 square millimeters. Now we could try for D10s, and that is 314 square millimeters, so not enough. For D12, and this is 452 square millimeters, so just over the minimum that we require. Now I'm going to split this in half somehow. I'm going to have my wall in there. Still, 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 still. And now we do section analysis. So that's our strain profile. This is step 4. My strain there is 0.003. This is C. This is the strain of the first bar. This is the strain of the second bar, and then the strain of the third bar, and so on. And then we have the distance. So we have 500 millimeters from that point, and this is 100 millimeters from that point. So basically that bar is 100 millimeters from there, and that bar is 500 millimeters from there. Sorry for the noise in the background. I think my cat is hungry. What I'm going to do is similar triangles. I'm going to use the strain in the bar number 1 and my strain in the bar number 2. So basically what I'm saying is 003 is 191.3, that's C. As the strain in the first bar is C minus the distance of the first bar. And then the strain of the second bar is equal to 500 minus C. From here we obtain E1, strain 1, epsilon 1, 0.0014, strain 2, 0.0048. So this is more or less a yield, and this is quite larger than yield. So what that means is that we have 1 bar yielding in compression and 3 bars yielding in tension. Now, if the strain of bar 2 was very close to 0, then I will calculate the strain of the bar number 3 there. So this is number 1, 2, 3, 4. And then I may have 1 bar yielding in compression and 2 bars yielding in tension. So now we can calculate, sorry, I forgot to obtain A, which is A1 plus A2, 162.6, and C, which is 191.8. Now we calculate the compression force coming from the steel. So that's 1 bar pi 6 square Fy. This is 33.9 kilonewtons. Now the tension force coming from the steel, which is 3 bars by 6 square 300, and this is 102 kilonewtons. Now the compression force coming from the masonry, which is 85 FIM a thickness, and this is equal to 232 kilonewtons. Now we need equilibrium. So basically we have that our Cm plus Cs minus T has to be equal to my axial load. This 3 is 164, and is not the same as 118. So we need to go back and recalculate A1, A2, and see. We are going to estimate it, or we are going to assume. Now, obviously, I've done this a couple of times until I got the right answer. I'm not going to do 3 or 5% here, but if I use A as 135 millimeters, C at 158.8 millimeters, then my compression from the concrete is equal to 192.8. We have the same 1 in compression, 3 in tension, so the loads are the same. And in this case, we have that Cm plus Cs minus T equals to N. So 124.7 is equal to 118, kind of. So we accept that. So that's our design. And now we can calculate the moment capacity. Again, strain compatibility. So we have 1 bar there, another bar there, another there, another there. 100, 500, 900, 1300. And we have our forces in there. So that's the compression force. We have N. We have the compression force from the steel, tension force from each of these bars. And then we can calculate Nm, which is, I'm going to go quite fast here. Second bar, third bar, and the excellent. And this is equal to 158.7 kilonewton-meters. So if we multiply by the strength reduction factor, it's 135 kilonewton-meters, which is larger than M star, which is 130 kilonewton-meters. I hope I didn't go too fast or too slow, and no one fell asleep in there. Now the in-plane shear. Let's see if I can make it on time. My B star is 104 divided by 2, 52 kilonewtons. My Vn is my V star divided by the strength reduction factor, 69 kilonewtons. My D from here is equal to 0.8 LW, which is 1120 millimeters. T is 140 millimeters, but my BW, because we have a partially grouted wall, is 60 millimeters. So because my handwriting is so bad, I use capital B, big, quite big for forces, and then for the small, for the stresses, I put these wings. Otherwise, I will mix the two of them all the time. So that's stress, that's force. So my Bn is equal to the force divided by my area, and this is giving us 1.03 MPa. This is smaller than 1.5, so the first check is passed, that one in there. It cannot be larger than 1.5. If it was larger than 1.5, then we need to increase the size of the wall. Now we calculate the stresses. So Vn is equal to the contribution of the masonry, contribution of the axial load, contribution of the steel. Now the contribution of the masonry is C1 plus C2 times VBM. Now C1 is equal to 33 PW times Fy over 300. Now this is equal to 1, obviously. My PW is equal to 4 bars diameter 6, radius 6, divided my gross area. This is equal to 0.0023. So this is equal to 0.076. Now C2 is equal to, because H over L is equal to 0.86, that means that C2 is 42, 4 minus 175, 1.2, 1.4. And this is equal to 105. So my VBM is equal to 0.7. This is quite simple, right? And then my contribution of the masonry is 0.076 plus 105 multiplied by 0.7. And this is equal to 0.8 MPa. This is smaller than what I need, which is 105. So I need to check how much the axial load on the steel is contributing. If the contribution of the masonry was enough, because we have fully grouted wall, then we would stop there, provide minimum steel reinforcement, and we're done. Let's check. I've done it on purpose, obviously, so I can show you the contribution of the axial load. So this is equal to 0.9 n star area and times the tangent of alpha. Now I'm going to do a little sketching here. That's my n. That's where the load is going to, which is half of A. That means that my alpha is there. That means that my tangent of alpha is equal to 1400 over 2 minus 135 over 2 divided by 1200. And then when we plug that in here, we get 37 MPa. I'm going quite fast here because I'm running out of time, and this is actually quite simple. So 0.37 MPa. Now, if we add the contribution of the masonry, the contribution of the axial load, this is larger than 1.3, which is what I needed to do. So I don't need to do the contribution of the steel, because any steel we have will already be sufficient. So what we do is minimum rear steel based on those provisions here. Those ones there. That's it. That's it. It's quite simple. Now, I'm gonna do the. I have two more examples in here. So this is what I just did. I have a returning wall, out of plane moment, out of plane shear. I will share the Word example with you guys, and then I have a third example in there, a little bit more practical based, I guess. Now I'm almost done. I have 3 slides on columns, and that's because they are so simple. I decided to make it quick. Right, so it's chapter 9, chapter 9.3. We have a similar limitation for the dimension. The numbers are slightly different. Instead of 120, now we need 240. And we have a specific criteria if we use ductile or ductile design. But we are focusing, remember, on elastic and limited activity. Now, longitudinal reinforcement, we have a criteria there, 1/4 of the smallest dimension of grouted space. So we usually combine these two, so we have that core fully grouted, or that one there. So 1/4 of the smallest grouting dimension, or 1/12 of the smallest column dimension. And we have also a reinforcement area limitation, a minimum limit and an upper limit, the minimum limit being just a number, and then depending on the area of masonry over the strength of the steel, and the upper limit depending on the grouting area over the yield strength of the steel. Then the transverse reinforcement, the stirrups, and we need to use at least 6 or larger than 6 if the diameter of the longitudinal bar is less than 20, and more than 10 if the diameter of the longitudinal bar is 20 or more. Now we have 4 criteria for the spacing. The smallest column dimension, so in this case it would be 390 because it's square. Half of the height, so if we had a rectangular column, that one might be different than that one, but in this case, the smallest column dimension, sorry, the half of the height is going to cover. And then we have 2 limitations based on the steel, 16 times the diameter of the longitudinal bar, or 48 times the diameter of the transverse bar. And then we calculate the capacity similar as before, the axial capacity times the strain reduction factor larger than the demand. The equation is different this time. It's basically the strength of the masonry times the area of masonry minus the area of steel. And I see a couple of questions there. I will wait until I'm done. It's the last slide. Plus the area of steel times the stress of the steel. And then for the moment, we actually have to go to chapter 10.2. It's very, very similar to walls using first principles. In this case, it's simpler because we will not have multiple layers of steel. So it's simpler than walls. And for shear, it's the same approach as per walls, but again, it's simpler because the format or the geometry is simpler. And that's it.
Yep. Thank you, Ralf, and thank you, Enrique. I found the presentations very useful and informative. I'm sure everyone else did as well. So thank you. And we will be sharing the recording with all our CSOC ESE members this month. So keep an eye out for that. And as Ralf mentioned, if you have any questions, feel free to send them to the CSOC email, or Ralph's or Enrique's or my email.